Let me welcome you to our lecture B5 in the Nanophotonics module. The lecture B5 will deal with starting the lecture to give you a little bit of an overview of where we are at with our module and emphasize a few relevant aspects about the delivery of our module. So first, you may have noticed that the way that we have structured the module is actually on big topics, topics A, B, C, D, and so on, which deal with major concepts in the field of nanophotonics. And as you have noticed already, the field of nanophotonics is rather heterogeneous in the sense that we are dealing with a variety of very fundamental aspects covering both electrodynamics and quantum mechanics. So in that context, our lectures are structured in lectures which introduce new fundamental concepts. These lectures are accompanied by tutorial questions to strengthen the understanding of these fundamental concepts. And to give a couple of examples here, we are talking here about waves in inhomogeneous dielectric materials. We are talking here about the concepts related to the transfer matrix method, and so on. There is a second type of lectures which are illustrative, and those lectures deal either with advanced recent developments in the field of nanophotonics. An example has been last time when we dealt with the 2D and 3-dimensional photonic crystals. Another example will be the one today when we're going to deal with the presence of photonic band gaps in aperiodic, in non-periodic materials. And in addition to that, we have lectures which have an application focus, as is going to be the lecture B6 delivered by Jeremy later on. This lecture as well does not have tutorial questions associated with them. It presents recent or fundamental applications of the nanophotonics concept, again, for illustrative purposes. And while the lectures in this class of new advances in the field of nanophotonics and application focus, they do not have tutorial questions associated with them. They are equally important because they let you build a general perspective on the field of nanophotonics, and in the meantime, allow you to understand at a deeper level the concepts that are going to be of use in some of your projects that you're going to do for the nanophotonics module. Now, that being clarified, I also want to talk to you about the lecturing structure and the amount of lecturing that you are getting. Each week, we present to you lecture materials worth about 2 hours of lectures, right? Just similar, I would imagine, with any other module. So we have 2 hours of lectures, but what we decided to do, based on the evidence that is now accepted within the academic community, is that it's better to split the concepts associated with the lecture in smaller chunks, such that it's easier for you to understand them and to digest and put them in the proper context. Adding together everything within a week of lectures, you should get no more, no less than 2 hours of lectures. Now, in terms of the tutorials for the week, each tutorial will follow the materials presented in those 2 hours of lectures, right? So we're going to have, and we have around 4, 5, 3, sometimes questions per week, depending on the size of the question and depending obviously on the concept presented, which deal precisely with the lecture presented during that week. There was a special case for week number 1, in which, given the fact that most of you have been away for a year dealing with your research project or dealing with your placements, we have decided that it's a good idea to put forward the concepts which we think are essential to revise for the nanophotonics module. So you know precisely which concept need a little bit more attention. We are aware that you have seen them before, either solid state, quantum mechanics, oscillation and waves, electromagnetism, but we want to go back and take a second look at them. Hence, for the first week, we had a little bit more material, but it was mostly revision material. So in a nutshell, for the week structure of the lecturing materials, lectures and tutorials, all of them cover 2 hours of lectures, and the tutorials reflect on those 2 hours of lecture. Doesn't matter how we split them, A1, A2, B1, B2, that's irrelevant. What matters is the total amount of information presented to you. I do want, though, to acknowledge that the current configuration is far from optimal. Unfortunately, we had the tutorial schedule on Tuesdays, which is just after the week has started, and I do acknowledge that you didn't have enough time maybe to peruse the lecture material such that you are in a good position to attempt the tutorial questions. So what I decided to do about that is first have a catch-up tutorial during this week 4, in which we'll not deal with new material. We had just 2 illustrative lectures, in which we're going to deal with questions from tutorial 1 to 3, or questions regarding the lectures presented in week 1 to 3. And you are welcome to bring your own questions. If there are no questions, I'll present a couple of questions myself. On the other hand, starting from week 4, we're going to make sure that we delay the tutorial such that you have enough time to see the lecture material. So there will be a shift, and we're going to make sure that you have 4 to 5 days of seeing the lecture material before attempting the tutorial question. So I acknowledge that that was an issue. It was a bit unfortunate that we had the tutorial schedule so early in the week. Okay, that being said, let me now move to what I would like to cover in this lecture. And in this lecture, as I mentioned, I would like to cover the aspects related to band gaps in aperiodic dielectric materials. This is a big name for non-periodic structures. Let me share the screen with you over here. Share. Okay, I hope you can see my screen. I will also shut down my video. And let us discuss the context in which we introduced these photonic band gaps in aperiodic dielectric materials. So we discussed up to this point in the B series of lectures, photonic band gaps and photonic crystals. So band gaps and periodically structured materials. We had 4 lectures, the first 3 dealing with the fundamental aspects related to one-dimensional structures and the presence of the gaps. We start with inhomogeneous media and the transfer matrix method, which generally apply to finite structures. And then in lecture 3, we introduce this periodic materials of infinite extent, which we call photonic crystals, in analogy with the atomic crystals, the usual electronic materials. In lecture 4, we extended these concepts to 2- and 3-dimensional structures. We show that in contrast to the atomic materials, for photonic structures to get band gaps in 2 and 3 dimensions is more challenging, basically because the electromagnetic field is a vector field, while in the case of the electronic problem, we have the wave function, which is a scalar quantity. Now we replace that scalar quantity with a vector quantity. We need to get band gaps along various directions, and hence this creates additional challenges. However, we've been successful in predicting band gaps in 2 and 3 dimensions, and we've shown how we can characterize them. So today, I'm going to further extend the concepts related to photonic band gaps in the absence of periodicity, dealing with materials which are non-periodic. Before doing that, I would like to present to you a few very beautiful examples of photonic band gaps which are present in natural materials, right? And they give rise to these beautiful structural colors. By structural color, we mean a color which is obtained in the absence of a pigment. Typically, in order to produce a color, we need a chemical compound, which we call a pigment, which absorbs light of a certain wavelength, and then emits back light of a certain wavelength. So, for example, a green material will emit back green light. In the case of the structural colors, and I start here with the example of opal, a semi-precious stone, we note that the colors coming out of the structure are first iridescent, so they depend on the angle at which we look at, and they present a variety of colors, from green, yellow over here, red, brown, and so on. And the mechanism through which these colors are produced is quite interesting. Upon close inspection, we note that the structure of the opal presented here consists of spheres, dielectric spheres, arranged in a periodic array. This is an FCC lattice of silica spheres of a radius of around a fraction of the micron. We know there are some defects on the surface, but inside mostly periodic structure. When the light comes, and let's imagine we are looking here at this green-yellow spot, when the light comes at a given angle of incidence, it encounters a periodically structured material, which can give rise to a band gap along that specific direction for that specific wavelength. So hence, light incidence at this angle of green-yellow color encounters a band gap and hence is completely reflected back, and we perceive the green-red color over here. Now, for a different angle of incidence, say one associated with this region, light of red color is incident upon the lattice. The lattice is arranged such that it presents a band gap for the red colored light. So we note that the reflection from this material depends both on the angle of incidence and on the wavelength of light. We call these band gaps formed in the structure either stop gaps or incomplete photonic band gaps. Why incomplete? Because they are present only for a certain frequency at a certain wavelength, at a certain incidence angle. And the reason behind not getting a full gap for all the wavelengths and all the angles is simply because the materials making up the structure, the silica spheres and the air, do not have an index contrast large enough to allow for the formation of the gap. We've seen in the previous tutorial that the band gap size is directly proportional to the index contrast between the materials making up the structure. So delta N, which appears in our formula. Well, delta N over here is between silica, which is glass, 1.3, 1.4, index of refraction, and air. And that is not large enough. Well, we obtain a very similar effect in biological materials like the needles of this sea mouse, which when observed under microscope display a almost perfectly periodic dielectric structure, and when light here of a green wavelength, so something around 550 nanometers, is reflected from these needles of the sea mouse creature, it's strongly reflected back because for that wavelength, the green wavelength, the structure presents a photonic band gap at that angle of incidence. And the same for this reddish colored region in the sample. Exactly the same mechanism, but now in a biological structure. And then finally, we have a quite interesting example associated with this morpho butterfly presented here, in which it has a beautiful blue coloring. We note the absence or the strong reduction of iridescence. So it's a relatively uniform blue color. You don't have the same kind of structuring as in the case of the opal. And upon examination of the structuring of the material making up the wings, we note the following. We know that it's not necessarily periodic. It consists of a network of struts connected at vertices not necessarily periodic, but in the meantime, having a certain uniformity preserved across the structure. And indeed, if we look at the structure factor, and if you remember from your solid state physics, a structure factor is basically a Fourier transform of the dielectric distribution. We analyze the dielectric distribution and perform a Fourier transform, and then come up with this structure factor, S as a function of K. And we note the complete absence of any Bragg peaks. Bragg peaks in the structure factor are associated with periodicity. Here, we got no Bragg peaks. So the structure is not periodic, but in the meantime, presents this structure in color. And this kind of guides us towards asking the question, what are the ground rules for obtaining structural color and photonic band gaps in materials which are non-periodic? Before dealing with that question, I would like to present to you some beautiful examples of fabricated photonic bandgap structures. And I start here on the left with a 2D periodic structure consisting of an array of dielectric rods, silicon rods in air. The index of refraction contrast between silicon, index of refraction 3.4 something, and air is now large enough to form a full photonic bandgap. We also note a different structure in which we have this arrangement of periodically arranged rods, but now we have introduced a line of defects, two lines of defects, which provide a waveguide. And what do I mean by that? When the light propagates along this line of defects, if you want to escape left or right, it can't, because there is a band gap. It's completely reflected back in the waveguide channel. So therefore, we are able to provide confinement and waveguiding through the photonic bandgap effect. In a similar manner, we can consider this membrane here periodically structured with holes in which the central hole, this one over here, is somewhat larger than the surrounding holes. This provides a defect mode, a mode in which we can localize the electromagnetic radiation. And the mechanism of localization is similar to the one discussed here. The hole, the larger hole, is surrounded by material which has a band gap. The light is reflected back to the central hole. And this provides what we call a cavity. I note also the dimensions associated with the structure, which are on a fraction of the micron. The reason for that is because there is a direct correlation between the size, the length scales in the structure, and the wavelength of light that it controls. In this case, we typically talk about controlling light at 1.55 microns, which is of interest in the telecom industry. In the meantime, we have three-dimensional variants. This wood pile structure, which consists of dielectric rods arranged periodically, but they are shifted in position with respect to each other. So this line of rods is shifted such that the road falls to the middle and so on in this direction, while in the perpendicular direction, we have a similar arrangement. We have various ways of producing these wood pile structures, another example shown here. And we have some other very interesting examples shown in this figure here on the right-hand side, in which what we do, we start with an opal structure. You see the structure here on top, which is precisely the structure that we see in the opal, arrangement of silica spheres in air, an FCC arrangement of silica spheres in air. And what we do, we infiltrate this structure in the voids, in the air voids, we place a different dielectric material, and then we etch out the original template of the silica spheres. And what we are left with is a structure shown here, which consists of air spheres, the spheres that have been etched out in a dielectric background. We call this an inverted opal structure. The advantage here is that when we do the infiltration, we can infiltrate with a material with a higher index of refraction, and hence we obtain the required contrast between the index of refraction of the air and the index of refraction of this dielectric material, typically silicon. In this case, we do have a full complete photonic bandgap, and we can introduce, as before, waveguides and cavities in this dielectric material to control the propagation and the confinement properties of light. Okay, so this is a place that we are starting with, and the question, the fundamental questions that we ask ourselves is it possible to predict photonic bandgaps in the absence of periodicity? And if so, how should we go about doing it? Because I don't want to predict a accidental structure, which is non-periodic and presents photonic bandgap, but actually I would like to introduce new classes of photonic bandgaps, which are non-periodic. In doing so, I would also like to explore what are the fundamental aspects which affect the presence of photonic bandgaps. For a given system, how can I identify the structures which are going to have a photonic bandgap? And as you will see, we're going to talk a lot about the role that is associated with the presence of short and long range order in the structure. What do I mean by that? Imagine you have a point in the structure and you look at the first set of neighbors or the second set of neighbors, and you look at how well are they structured. What is there some order? It needs not to be perfect periodic order, but rather than that, some sort of uniformity. And at the same time, I look at the effect of this order on long range, so from across the sample. And this is directly related with our view on the formation of photonic bandgaps in periodic structures. So if we step back to the lectures that you've seen in the B series, at the beginning of the B series, we made an argument that in order to get a bandgap in a periodic dielectric system, and I have here an example of a one-dimensional photonic crystal, epsilon 1, epsilon 2, epsilon 1, epsilon 2, so on, periodic repetition of a unit cell. And then there we said that when we discuss a Bragg frequency, we said that the Bragg frequency is given by the following condition. If I look at the unit cells inside the crystal, I impose a condition that in the first unit cell, so the first unit cell consists of this slab of epsilon 2 and a slab of epsilon 1, the light reflected by this first unit cell and the light reflected by the second unit cell and the third unit cell and so on need to be in phase. If they are in phase across the crystal, then that happens at the Bragg frequency with a condition given over here, and the structure is going to strongly reflect all the light at that frequency, shown here, a strongly enhanced reflected signal. And hence, if the reflected signal is enhanced, propagation becomes harder and harder until it stops. So we get a bandgap. Nothing is propagating forward, everything is reflected backwards. Now, I'm going to call this condition Bragg scattering, because it's associated with a scattering within the unit cell, and I'm going to regard it as a large-scale resonance of the array of particles. Everything in the array matters. Every single unit cell needs to scatter in phase backwards to the radiation in order to get a bandgap. So it's associated with the whole array of scatterers. In our discussion of bandgaps during last week, we also discussed a second condition, and we call it there the quarter wavelength condition, the QVS, right? So what did the quarter wave stack condition, right? What do we mean by that? Well, what I mean by that, if you remember, we said, okay, we are happy with the Bragg scattering, but now I want something more. Within the unit cell of the array, over here, one unit cell, a dielectric material and air, I want the light scattered within each of the pieces of the material, dielectric and air, to be in phase with the light that was reflected as a top interface. So light scattered over here is in phase with the light reflected, and hence each piece of the material contributes to the reflected signal. I impose the same condition for the air fraction of the material. So light scattered as an interface here between dielectric and air, and the light that has propagated in air and came back need to interfere constructively in the reflected signal. And I call this a small scale resonance of the array. Why? Because it refers what happens within each piece of the material associated present in my array, right? So it's not across all the array, but rather than in the individual pieces of the array. This gave rise, as we discussed before, to this quarter wavelength condition that the optical path in each dielectric, being the solid dielectric or the air, needs to be equal and equal to a quarter of the wavelength. So now, if I put these two conditions, large-scale resonances of the array and small-scale resonances of the individual scatterers together, and I ask for them to happen exactly at the same frequency, I obtain not only do I obtain a band gap, but I obtain the largest band gap possible in that material. And I'm going to say that the Bragg scattering, the one presented here, and the Mie scattering, the one presented here, reinforce each other to produce the largest gap. And this is the traditional, the conventional picture that we develop in this module regarding the origin of the photonic band gap. There is a different picture, which you probably have encountered in solid-state physics when discussing the formation of crystals. So let us imagine that we have a single atom, right, with electronic levels, right? So we have an atom, like, I don't know, copper atom, and we are looking at the atomic levels, electronic levels inside the atom. We're going to have a ground state, which I show here in red, right? If I look at the ground state and I plot the wave function for it, I get this red curve, which tells me that the wave function has a maximum at the position of the atom. Now, what happens when I put more atoms together? Well, when I put more atoms together, they become coupled to each other, they talk to each other, and instead of the single states that I had before, I'm going to get an ensemble of states which form a band gap. Because of the coupling, they no longer have the same frequency, the same energy, but rather than that, they hybridize and they form a band of states, right? Now, let us think about adding the first excited state in the problem. Well, if I consider adding that state, let's consider it to be this green state over here. If I plot a wave function of this state, typically it has a node at the center of the atom. Then if I put them together, as coupling many atoms together, what will happen? This excited state will evolve into a band of states shown here in green. Now, if the coupling is not, if the states associated with the system are very uniform, the coupling is moderate, what happens is that I have two bands, the red band and the green band, which remain separated by a spectral region, which represents a band gap, right? So I have bands of states, red and green, separated by a band gap. Well, this was a structure that we built for atomic electronic systems. And you note that in my argument here, I didn't rely upon periodicity. I said about bringing atoms together to form a compound. I can apply exactly the same concept, but now for photonic materials. So what I'm going to say is that I take a single scatterer and I look at the resonances. What does a scatterer resonance mean? Well, it means I send light. Imagine I have a sphere, a dielectric sphere. I send light, and for a certain wavelength of the light gets coupled inside the sphere, bounces around for a very long time, and then it may eventually come out of the sphere. So I call the resonance the fact that the light becomes trapped inside the sphere for a long time. And if I do the same experiment and I send light of a different frequency, I will note that I obtain for the lowest energy frequency state, I have the first resonance with the field concentrated around the middle of the scatterer, and I call this first Mie resonance. The second resonance with a field having a nodal plane through the scattering, very similar to the electronic states in an atom. And then if I put them together to form a solid, I get exactly the same principle behind the formation of the gap. The ground states, the first me-resonance states, evolve into a band that will be the first band of the system. The second me-resonance evolve in a second band that is going to provide a band gap as a separation between the two bands. So I get a second mechanism regarding the formation of band gaps, which does not rely upon the periodicity of the system. Okay, so now with these two pictures, one based on periodicity, one based on just bringing scatterers together, I want to move on and be in a position to predict which aperiodic structures have a photonic band gap. And to do that, I need something else. What I need is, what are the optimal structures? So if I think about periodic structures and I want to evolve to aperiodic to non-periodic structures, what are the optimal platforms upon which should I base my design? And I'm presenting here the optimal platforms for periodic structures. So if we want a band gap for the TM polarization, TM, it means that the electric field is oriented along the direction of the cylinders. So if I want a band gap for this TM polarization, what should I do is, what the optimal structure consists of is this arrangement of dielectric rods in a periodic array as shown here. Indeed, if for this structure, I calculate the TM modes here presented in red and the TE modes, TE, the electric field is in the plane, I obtain that I have a band gap, absence of modes, for the TM modes and no band gap for the blue modes. We note that here all the bands, the blue bands, overlap with each other. In contrast, if I want a band gap for the TE modes, I should use this network architecture shown here, which consists of air holes in a dielectric material. And indeed, if I calculate the band gap for the blue modes, the band structure for the blue modes, I note the presence of a sizable band gap here, no blue modes in the spectral region, but the absence of band gaps for the red modes, which are the TM polarization with the electric field parallel to the direction of the holes. If I want the band gap for both of them, TM and TE, what I do, I enlarge the radius of the holes. And you see, if I enlarge it quite a bit, I obtain a structure, the one shown here, which has network architecture, but at the vertices, you see the formation of the scattering centers, which play a similar role with the one played by the rods. So the network is going to give rise to TE band gaps, while the scattering centers at the vertices are going to give rise to the formation of TM band gaps. And indeed, the band structure for the structure shown here presents a common band gap for the TM and the TE polarization. And moving forward, these are the optimal designs. These are the best known architectures for formation of band gaps in periodic structures. And as I move away from periodicity, I'm going to try to rely upon the design principles for these structures. And the first step is to consider what we call quasi-periodic structures. What are quasi-periodic structures? And I present here an example of the Peros lattice, which consists of this arrangement of tiles. They are called fat and skinny tiles. And there is a general set of rules of how to arrange this set of tiles such that I can cover the whole 2D plane. Obviously, the structure is non-periodic, but interestingly enough, if we perform a Fourier transform on it, which is shown here, it shows the presence of tenfold symmetry. What does that mean? It means we have peaks, Bragg peaks, arranged in a 10-fold symmetry. So 360 divided by 10, 36 degrees between the peaks. Now, this type of symmetry is forbidden in any periodic structure. In periodic structures, we can have 4-fold, 6-fold, and so on, but not beyond 6-fold symmetry. So clearly, this was, at the time when it was discovered by Sheckman in '84, a big mystery. So they observed the presence of these 10-fold symmetric peaks in some metallic compounds, and this was not only a mystery, but it was completely forbidden by usual crystallographic theory. Well, Sheckman and later Steinhardt introduced this concept of quasi-crystals, which can explain the presence of these 10-fold symmetric peaks. And Sheckman got the Nobel Prize a couple of years before, I think it was 2011, in chemistry for the discovery of quasi-crystalline materials. For our purposes here, what we would like to do is use the structure here to make a photonic bandgap, right? Because we know that quasi-crystalline structures have Bragg peaks, so there is Bragg scattering in them. It's not periodic, so it's like the first step beyond periodic materials. And the approach that we are going to use is to take the position of the points predicted in a, say, Penrose lattice and place dielectric cylinders at those points, right? So wherever we have a point, a dielectric cylinder, the resulting pattern is going to be non-periodic, is going to have this higher symmetry, which is crystallographically forbidden, and we would like to find out if they have band gaps. Now, you may wonder, how do you generate the quasi-crystalline point pattern itself? You can do it with this arrangement of tiles, but this is very particular to the Penrose pattern. And there is a general method of generating these aperiodic, quasi-periodic point patterns, and is what is called a strip projection method. Imagine that instead we want to generate a point pattern like the one shown over here, which is aperiodic, is quasi-periodic in one dimension. So along a given direction, I want to generate a aperiodic point pattern. How do I go about it? Well, it's relatively simple. So you go one dimension higher. So from 2 dimensions, from 1 dimension, I'm going to go to 2 dimensions, and I'm going to generate a periodic lattice in 2 dimensions, 1 plus 1. 2 dimensions. So this is a periodic lattice in 2 dimensions. And then in this periodic lattice, I'm going to choose a direction, this one in black over here, which is oriented in a irrational fashion with respect to the periodic lattice. And what do I mean by that? So imagine that when I calculate the angle made by this line, this direction, with the direction of the axis of the periodic lattice, if the line passes through a point of a lattice, I'm going to get the slope given by a rational number. So it's going to be whatever, 5 units in the vertical direction and 3 units in the horizontal direction, or whatever combination I get, right? If I orient the line in an irrational fashion, it's never going to pass through any point of the lattice. It might become very close to it, but never through the point, which it means that the tangent of this line is going to be an irrational number, right? Very good. In the case of the Penrose lattice, this irrational number is related to this tau written here, 1 plus square root of 5 divided by 2, the famous golden ratio. So once we have this irrational direction, in the perpendicular direction, I'm using a unit cell. So this square, you see it? And what I do, I move this square along the line, right? And whatever points fall within this region, so these blue points over here, they are within the region span in the parallel direction, I project them on the line. So this point over here, it's within the domain, it gets a point on the line. This point projected, and so on. So I go on doing that, and then I look at the pattern generated along this line. And that pattern will provide me an example of a one-dimensional quasi-periodic point pattern. In this case, it would be simply the famous Fibonacci set, right? But this is a general methodology. And not only that, but I can create periodic approximates to this pattern. How do I do that? Well, imagine that this is the orientation of the line, is irrational, it doesn't pass through any point. But then I say, well, if I move the line a little bit to the left or a little bit to the right, I can make it pass through a given point. And that will create an approximation of the Fibonacci set, right? Very good. Now, I won't go into all the details, but then if I have this, I can look at the distribution of the distances between the points in the pattern. And I will have a set of long, what I call long, short, long, short, long, short distances, again, reproducing identically the famous Fibonacci set. And then I can consider this to be my one-dimensional system, right? So it's going to be, instead of being periodic, having long, short, long, short, long, short, is going to have a different arrangement. And the question is, does it present a photonic bandgap? Now, we can extend this to 2 dimensions. It's the mathematical formalism is much more complex. I won't go into the details of it. I will just tell you the story. I want a 2-dimensional quasi-periodic point pattern. I will go into lattice in 5 dimensions. And in 5 dimensions, I will consider 2 spaces. One of them, the 2-dimensional space, and another one, a 3-dimensional space. 2 plus 3 makes 5, exactly the dimensionality of the hyperlattice I start with. And then what I'm going to do, exactly the same procedure that I have here. I decide upon a unit cell in the parallel space, and I project everything that I get in there on the perpendicular space. If I do that, I end up exactly with the Penrose lattice. And again, as I noted before, not only that, but I also can create periodic approximates of this perfect quasi-periodic lattice. So this is the Penrose lattice shown here, and these are various approximates of it, which are now periodic. They are as close as I want to the exact lattice. Anyway, coming back, I want bandgaps in this structure. Well, I do what I decided before. I use the ideal structure for periodic systems, and I implement that design on the quasi-periodic point pattern, and I get the structure shown here with dielectric cylinders at the position of the atoms. Now, I performed the band structure for this lattice, shown here a fragment, right? Dielectric cylinders of radius 0.17, and what I obtained is a very large photonic bandgap. Despite the system being non-periodic, I have a bandgap at around 40%, right? It's quite interesting because the bandgap occurs at the band here, which is precisely given by the number of points inside the pattern. So here we have 200 cylinders. The bandgap is band 200, which tells me that actually this comes from the fundamental resonance inside each of the cylinders. Now, what about TE photonic bandgaps? Well, for TE photonic bandgaps, what we do, we actually create cells around each of the point of the Penrose pattern. So here, as the center of the cell, in each cell, we have the point associated with the Penrose pattern. We create a cell around it, and then we obtain a network, this trivalent network shown here. If we calculate the TE bandgaps for this structure, we obtain a beautifully defined 42% of the central frequency, extremely large photonic bandgap, which has the very same property. The band at which the bandgap occurs, the band number over here, it's equal to the total number of cells now in the structure. So clearly, this is associated with the resonances supported by individual cells. Now, what if I want complete photonic band gaps. Well, if I want complete photonic band gaps, I need to combine the designs of the two. And here we adopt quite a simple procedure. At the vertices, I place cylinders, and along the edges, these dielectric walls. And indeed, I obtain a band gap, which is now at band 600, and it's about almost 16.5%. Again, a very large photonic band gap. So we note that the periodicity is actually not a prerequisite for the formation of the gaps. We get photonic band gaps in aperiodic structures, in quasi-periodic lattices. But now the question is Bragg scattering playing a role? Because we saw that for quasi-periodic structures, while they are not periodic, there is Bragg scattering embedded in them. And they are called, because of the Bragg scattering, they are called to have long-range order in the structure. So there is a deterministic way in which we generate these structures. And we saw that through that projection mechanism, everything is fully determined. There is no randomness present in the material. The question is, can we generate a structure which is non-periodic, neither periodic nor quasi-crystalline, which shows a band gap? And for that, I'm going to focus on the next slides on the concepts associated with the hyperuniform structuring. All right, so let us now continue with our quest to identify systems, aperiodic, which present photonic band gaps. Putting together what we learned up to this point, we learned that photonic band gap is formed under the action of two main physical principles. One of them is related to the interplay between the microscopic resonances associated with scattering within the unit cell, which we termed as misscattering, and another one associated with macroscopic scattering, related to the scattering throughout the crystal, which we term Bragg scattering, which is directly related to the periodicity or the long-range order that is present in the system. Now, in the case of the quasicrystals, we've shown that while there is Bragg scattering, because we have Bragg peaks in the diffraction pattern, the role of the misscattering is now dominant and takes precedence over the Bragg scattering. And the question to be addressed is there a general class of aperiodic structures which allow for the formation of the band gap? And I will show here that there is indeed a fundamental correlation between geometrical properties like uniformity and the photonic properties like the presence of a gap. Within our discovery, we're going to show that there is a general connection to the problem of tiling the space uniformly with generic tiles and the presence of photonic band gaps. So as we move to completely non-periodic structures, we're going to take with us two essential elements. We're going to replace the periodicity, be it local or general throughout the structure, with a concept of local and global uniformity. So we relax periodicity constraint to a lower constraint associated with uniformity. We're also going to introduce some generic disorder point patterns and the photonic structures associated with it. And I want to mention at this point that our discussion is related to generic classes of photonic band gap material rather than very specific examples of accidental structures which present photonic band gaps, as one referenced in the papers over here. So our approach is quite simple. We distribute in a disorder fashion points in space, and then we associate with each position of a given point the presence of a dielectric cylinder. The structure of the distribution of points in space presented here is associated with what we call the hyperuniform point distributions. These are disordered distributions of points which can be made as uniform as we like. And we have this chi, or the parameter, which tells us how disordered the structure is. And I present here the band structure as a function of this hyperuniformity order parameter. And we note that for values at around 0.3, 0.5, we open large photonic band gaps, which all of them are associated with the individual resonances present in the cylinders making up structure. At chi equals 0.5, the pattern is shown here, and the band gap size is at around 37% of the central frequency. This is a very large photonic band gap present in a disordered structure. It's not completely random. The structure is not completely random because there are correlations which do not let the points get too close to each other. In the meantime, there is absolutely no Bragg peaks in the refraction pattern. And indeed, if we analyze the modes present in the structure in this disorder pattern, we note that for modes below the photonic band gap, so modes, page down, modes in this region below the photonic band gap, what we note that is that their structure shown here for this mode inside the band gap and inside the band structure, and this mode exactly as a band edge, the modes proceed through exciting resonances in the individual cylinders. If I look around, yes, there is field which has a maximum value at the center of the cylinder. The same story here, where we have alternating positive and negative values for the electric field, but both are localized within the dielectric cylinder. If we move now to modes above the photonic band gap, modes in this region, we note that the structure is very similar to the second Mie resonance, in which we have a nodal plane through the cylinders. And indeed, most of the cylinders have a nodal plane passing through them. This happens also for the mode localized precisely as a band edge of the crystal. So this is a story for TE polarization mode, TM polarization modes. What about TE polarization? Well, in the case of TE polarization, we know that the optimal structure needs to consist of a network, connected dielectric network of material, and we obtain a very similar story in which the band gaps exist around the central frequency, and they are strongly enhanced as we increase the hyperuniformity, this uniformity that is present in the structure. And indeed, we obtain for hyperuniformity of 0.5, band gaps of around 36%, again of a similar size with the one found in periodic systems. Throughout the evolution, we maintain the position of the band gap at band number equal to the total number of cells present in the system, which means that the band gap origin can be traced to the individual scatterers in our system. And indeed, if we analyze the field distribution of this mode, we note that for the TE polarization, the H field is distributed for modes below the photonic band gap within the cells of the system, shown here, while modes above the photonic band gap have a nodal plane passing through each of the cells. So clearly, for modes below the gap, we put together, create an ensemble of resonances which excite the inside of each of the cells, while modes above are created by putting together ensemble of resonances through excitation with a nodal plane in the middle of each of the cells. Now let us think about propagation So if we think about propagation in such a system, I can imagine that the radiation, for example, propagates to the right by exciting resonances with main localization of the field inside the cylinder. So I have almost parallel planes propagating in the forward direction. Upon close inspection, indeed, each resonance is similar to the first resonance supported by the cylinder. And I have here a nice animation which doesn't work. That's okay. So we had some animation for the field, which shows the propagation inside the material. This one works. This is one for a photonic band gap. And you see the field comes, propagates inside the first couple of layers of the structures, and then is eventually completely reflected back in the direction it came. If we move to modes above the photonic band gap, as we argue, the propagation happens with modes that excite nodal plane inside the cylinders. And let's see if our animation works. Well, apparently not. The animation would have shown a propagation in this regime with nodal planes through the cylinders. What are possible applications of this? Well, imagine now I have a disorder surround in which I form a waveguide bending at completely arbitrary directions. Now it becomes possible because if I have a periodic structure, I need to provide the bending of the photonic waveguide only at axis of symmetry along the symmetry of the original crystal. So for example, in a square lattice, I need to bend the waveguide at 90 degrees, while in hexagonal lattices, I'll need to bend it at 30 or 60 degrees. In the case of disorder structures, I can create an arbitrary bending of the system, and as shown here, the light propagates along the waveguide with minimal losses in the background region. These structures predicted here have been fabricated in practice. So these are 3D printed square lattice, triangular lattice, Penrose lattice, and hyperuniform disorder lattice of these materials. And this presented here in the second row is a transmission measured through the sample. So transmission means as a function of the angle, so we go around 360 degrees, and as a function of the frequency in the radial direction. Wherever I see regions of blue color, it means that the transmission is low. It means we have a photonic band gap. And I note that for the square lattice, the transmission regions for which we have low values, so the band gaps, are respecting the square symmetry of the lattice. But I also note that if I want a band gap at all frequencies, I should have a circle here because I would want to obtain a gap that does not depend on the angle. So for square lattice and to some measure for triangular lattice as well, the position of the gap of these blue regions is strongly dependent on the angle at which we are measuring. Here, it happens at this frequency, while a normal incidence, it happens at a different frequency. Now, if we include Penrose lattice, quasi-periodic systems, we note that now the symmetry has been enhanced. So I have 10-fold symmetry instead of 6-fold symmetry or 4-fold symmetry. But still, there is certain asymmetry associated with the propagation. In the case of the hyperuniform lattices, this asymmetry has been removed, and I have nearly perfect radial symmetry of the transmission. So it means that for a frequency in this range, the band gap occurs exactly at the same values for the frequency, regardless of the angle we are looking at. And these properties, photonic properties, follow quite closely the scattering properties of the system. This is a two-dimensional structure factor, just a Fourier transform of the dispersion present in the structures. We can go further on and take the fabrication process from 3D printing, these are macroscopic structures, centimeter scale, to micron scale structures. These are structures fabricated on a micro scale. So you note here that the length scale here is 2 microns, which allow the propagation of light through these microscopic domains. These have very important applications because they deal with frequencies close to the 1.55 microns, which is a wavelength of most used in the telecommunication applications. And these are examples of structures that have been fabricated on these membrane silicon platforms. This is a platform in which we have a small amount of silicon in the vertical direction. It has been etched underneath, and it's in a membrane configuration without any contact with a substrate. So the light propagates solely through this waveguide channel presented here. We can also create cavities. We can put them together in a nice photonic circuit as shown here. But now the question is, as we have created this disorder photonic bandgap materials, has nature beaten us to the task already? Well, indeed. Maybe if you remember the first example with the butterfly wing of the morpho butterfly, we had there some structuring that seemed to be in disorder, but still presented photonic bandgaps. This is another example where the mandrill blue facial skin, so this portion over here, which if analyzed under the microscope, it shows a nearly perfectly hyperuniformly structured material. This is compared to some of our models that we use for those 3D printed structures. It's very close similarity. This is a diffraction spectrum associated with the mandrill skin, while this is the diffraction spectrum associated with this hyperuniform disorder lattice. So there is a clear connection between the bandgaps in disorder structures and the bandgaps in biological tissue. Now, finally, and I will have just a few more slides here, what I would like to discuss is another exercise of our imagination in structuring materials. For example, dealing with the diamond structure. You know that the diamond material is structured in a fourfold connectivity manner. This is the typical FCC lattice along which one forms a diamond network. So we connect through the faces associated with the Brillouin zone, with the Wigner-side cell of the FCC lattice. And if we put them together in a lattice, we form this diamond network. And the question that we want to ask is it possible to form disordered versions of this diamond network? And indeed, research shows that we can form these disordered networks of the diamond structure. And these were very useful in the early stages of analyzing the amorphous silicon material. You know, amorphous silicon, it's in the silicon same group as diamond, has a very similar structures. And in solar application, for example, where we cannot afford to use crystalline silicon, it's very useful to use this amorphous silicon material. But the question is, what is the structure inside the amorphous silicon? And studies have shown that there are very good models using these disordered networks of the diamond structure. Now, for the photonics problem, there is some very important characteristic related to diamond. If you go to 3 dimensions and ask what is the structure presenting the largest photonic bandgap in 3 dimensions, it turns out that is precisely the structure based on this diamond network. So if we arrange dielectric material as shown here in this diamond network structuring, the photonic bandgap associated with it is the largest. For example, if we are to use silicon to make such a network, we obtain a band gap at around 30% of the central frequency, which is by photonics measure a very, very large value. Now, the question is, what makes diamond special? Right? Why diamond? And we have answered this question by showing that if we are to characterize the diamond network as shown here, it has the highest degree of isotropy as a network. We call this structuring of the diamond network strongly isotropic. So it's a strongly isotropic network. Now we have shown that there is another network which is not present in electronic materials, which we call the trivalent network, shown here, which has trivalent connectivity. You note that for the blue structure, we have 3 of these roads connected at each vertex, and this gives rise to what we call the trivalent network. So instead of having 4-fold connectivity, it has 3-fold connectivity. Now, the trivalent network, if we analyze its isotropy, we find that it has exactly the same value as the isotropy which characterizes the diamond network. And in the meantime, we can create disordered versions of this trivalent network, just as people have created these amorphous networks to model the silicon. And the point that we take forward is that the band gap size, we calculated the band gap for both diamond and trivalent and obtained very similar values, seems to be related to the geometrical properties of the structure rather than the FCC-BCC symmetry. So it's very clear now that if we design structures which are not periodic, but rather than that disorder, we call them amorphous diamond, amorphous trivalent, they should present large photonic band gaps as long as the degree of isotropy present in the network has very large values. And indeed, by 3D printing in alumina is a material of high index of refraction for microwaves. It's like the materials, it's a ceramics, the materials the cups, teacups are made out of. If we 3D print these structures, we obtain that both the periodic and the disordered variants of the structures present very large photonic band gaps. Again, we measure the reflection from the structure as a function of the angle and as a function of the frequency. And we obtain a nearly perfectly circular photonic band gap, which tells us the structure is strongly scattering and is strongly isotropic. In the meantime, as always, we ask the question if the nature has beaten us to the task. And indeed, there are certain species of butterflies, like this Calophrys greeneus, which is a green streak out of South California. If we analyze under the microscope the structuring of these beautifully colored green wings, we know that they are extremely similar with the models that we come up with. And indeed, the reflection from the structure presents a very good match to our simulations. And I will end up here by saying that, as always in research, it's possible to take the lesson learned out of well-studied photonic materials, like the photonic band gaps present in periodic structures, and extend them to other type of structuring, like the aperiodic, in which we do not have a periodic repetition of unit cell, but we rather have a uniform arrangement of scattering centers. And we always keep an eye on both aspects, one of them of fabricating these structures for technological applications, and another one of understanding the structuring that is present in biological or natural materials, and see if we can learn any lessons from that. And I will stop here the lecture.